This is Unit 2D, Example 1, looking at areas under density curves. This graph at right is a histogram of vocabulary scores on a standardized test taken by all 7th grade students in Gary, Indiana. So there were 947 students total in the 7th grade. The smooth curve, that's this red curve, is a density curve drawn to show the overall shape of the distribution, and then we see the histogram is the bars. A quick check shows us that the scale goes from 2 to 12 and that it looks like each bar is 1 score width wide. So in question A, we describe the shape, range, and center of the density curve. So this curve is close to symmetric. The center looks to be between 6 and 8, so we'd say the center looks to be the score of 7. And the spread ranges from 2 to 12. 100% of the 7th grade students are included in the data. 287 students, we're told, had a vocabulary scores of 6.0 or lower. What percent of students had vocabulary scores 6.0 or lower? So we can, with a pencil, shade the bars representing these students. So if you come over, here's a score of 6, and so on your paper you could shade all of the bars 6 or lower. So that would be anyone from a score of 2 to 6 here. And so we see 287 out of 947, or as a proportion or decimal, that's 0.303. As a percent, that's 30.3% of students scored 6 or lower. So when we're calculating the percent or the area on the graph, we want to take the values and make a fraction to find the percent. If we want to think about what percent of students had a vocabulary scores higher than 6, we know that's going to be everything that we didn't shade over on this side of the graph. So we know there's 100% total students in our distribution graph here. So instead of trying to count bars, we can make things a little more simple on ourselves by calculating 100% minus 30.3%, and our total is 69.7% of students. So that's the remaining part that scored higher than 6. In statistics, when we do calculations using the fact that everything has to add up to 100%, we say we're using the complement. So we'd say 69.7% is the complement of 30.3% because they total up to 100%. Then we're told 635 students had vocabulary scores of 8.0 or lower. What percent of students had vocabulary scores higher than 8.0? So we can subtract 947 minus 635 to figure out 312 students scored higher than 8.0. And then we can use that 312 out of 947 to figure out the proportion, 0.329, or as a percent, that is 32.9% of students scored higher than 8. Remember, when we go from a decimal to a percent, we're multiplying by 100, which is equivalent to making the decimal point 2 places bigger. Example 2 gives us another density curve, but notice this is what we call a skew density curve. It's got a tail out here on the right side, so we say this is a right tail or right skew density curve. So the graph below shows the mileage per gallon, MPG for short, of 100 cars randomly selected for a mileage audit by the Environmental Protection Agency, EPA. The graph includes both the histogram data and the density curve drawn to match the distribution of the bars. So we've got the density curve in green over the bars, and then we also have the frequency table. So often before we make a histogram, we'll make a table of our values to help us draw the histogram. So this is called the frequency table. And we notice the vertical axis is measuring the frequency because we're working with a histogram, which is always that case. So we want to describe the shape, center, and range of this histogram. So the center of the histogram looks to be about 20, or somewhere in the bin from 17 to 21 miles per gallon. There are 100 cars in this data, and the middle is the 50th car. So we can check, oh yeah, the middle of the median is going to be in that 17 to 21 miles per gallon bin. Notice, 18 plus 39 totals more than 50, so we've got more than 50 cars in these first two bars. So the 50th car is somewhere in here in the bar from 17 to 21 miles per gallon. We'd say the shape is right tail or right skew, since there are a few cars with very high mileage per gallon, but most cars are between 17 to 26 bars over here in those bins. And then the range is the distance from lowest to highest, so the range is from 12 miles per gallon to 41 miles per gallon. And you could subtract those values. You could figure out, well, how far is 41? Subtract 12 to get a numerical value for the range. So the EPA is concerned about cars with mileage 21 miles per gallon or less. So using the histogram bars to count, what percent of cars in this random selection have this mileage of 21 miles per gallon or less? So using our frequency table, we know 21 miles per gallon or less includes the bins from 12 to 16 and 17 to 21 miles per gallon. So adding up the frequency in those bins, we've got 18 plus 39 equals 57 cars in these bins. So we know there's 100 cars total, so we come to our fraction, 57 out of 100, which as a decimal is 0.57, or 57% of cars in this random selection have mileage 21 miles per gallon or less. And in this case, because our denominator is 100, these are nice calculations. Rarely are we going to have our denominator 100, so typically we'll have to use our calculator to divide to figure out these proportions and percents. The EPA goal is for a majority of cars to have mileage 27 miles per gallon or higher. So we want to know what percent of cars in this random selection meet the goal, and is this a majority? So we see 27 miles per gallon or higher includes the bins from 27 to 31 miles per gallon, 32 to 36 miles per gallon, and 37 to 41 miles per gallon. So if we add up, there are 9 plus 5 plus 2 equals 16 cars in these bins. So 16 out of 100, or 0.16, is 16% of cars in this random selection have mileage 27 miles per gallon or higher. So this is less than 50%, so we don't have a majority, and the EPA goal is not met in this random selection. Question D asks, how do the histogram bars compare to the area under the smooth density curve? Does the smooth density curve seem like a pretty good fit or poor fit? So if we look back up, we see the histogram bars are a close fit to the smooth density curve, but not a perfect fit. So in some cases, the histogram bars are higher than the curve. In some places, the histogram bars are below the curve. So the histogram bars would have to have a narrower width to be a better fit to the curve. This should just say below the curve, a little typo there. Okay, so make sure you pause and record notes in your notes in case I'm reading more quickly than you can write. So take a minute, pause, and get these notes down. Okay, example 3 is areas under what we call uniform density curves. So have you ever wondered what would happen if you rolled the same game die over and over again? So if the game die is fair, we expect each side or face has an equal chance of coming up. So this graph at right shows the distribution for rolling a fair game die 100 times in a row, and then repeating that 1,000 times, or we say 1,000 is 10 to the third power, right? 10 times 10 times 10, 3 times is 1,000. So you can see the one face came up a bit more than 16,000 times, and you can see, they're kind of up and down, but they're all each close to 16,000 times. And this graph looks, we say, drastically different than the previous graphs. So we say a continuous random variable has a uniform distribution if its values are spread evenly over the range of probabilities. So the graph of a uniform distribution results in this rectangular shape. So notice our x-axis is measuring the number for the face of the die, and then the y-axis is counting the occurrences, right? And the 10 to the third means it's counting in terms of thousands. So our first question is, does this uniform graph satisfy the requirements for a density curve? So we want to check to see if the graph has our two density curve requirements, only positive y values, and does it contain 100% of the population data? And you can round to the nearest whole number if we're trying to estimate. So the bars for each face are all around 16,000 occurrences, in fact, a little bit higher than 16,000. And we can check, well, 100 times 1,000, that's 100,000 occurrences total that we expect. And then if we say it's even, 100,000 divided by 6 is right around 16,666.7. So that matches what we're seeing in the heights of the bars for the different faces. So it does look like the graph contains 100% of the population data, all the occurrences. And then we also see the graph has only positive y values, right? Our count is positive numbers, so there's no negatives involved. So this graph does satisfy the requirements for a density curve. The proportion of die rolls that are between 3 and 5, including the 3 and 5, so that would be rolls 3, 4, or 5, can be found by calculating the area under the density curve between the face 3 and the face 5, and then dividing by the total you found in part A. So our total is at 100,000 rolls. So we want to think about what is the area and does it match what you expect. So estimating the heights of the bars, the height between 3 and 5 appear to be, and I rounded quite liberally, around 16,000 plus 16,500 plus around 17,500. So that totals 50,000 occurrences of faces between 3 and 5. So that area, if we divide it by the 100,000 total, well, 50,000 divided by 100,000 is 1/2 or 0.50 or 50%. And this matches what we expect, that half of the time these three faces, 3, 4, and 5, will occur if the die is fair. Another way to think about it is we expect each face to come up 1/6 of the time. So 3/6 is 1/2. That's another way you could think about it. Question C tells us Chandra is in a heated board game with friends and needs to roll a 5 or higher to win. So what proportion of die rolls should Chandra expect to be 5 or higher? So since our distribution is uniform, we expect all faces to occur an equal 1/6 of the time. So Chandra expects the 5 face to occur 1/6 of the time and the 6 face to occur 1/6 of the time. So we can say, oh, Chandra expects 1/6 plus 1/6 or 2/6 or 1/3 or 0.33 as a decimal of the die rolls to be 5 face or higher. So Chandra needs this 5 or higher to win, so we expect she's got around a 1/3 probability or 1/3 proportion of winning. Question 4, or example 4, looks at the mean and median for density curves. So the mean is another way of saying the average, remember. And the mean of a density curve is represented by this Greek letter mu, and it looks like a cursive M. And we can think on the graph of the mean as the point at which the curve would balance if it was made of solid material. So like a teeter-totter, it's the point where you would get both sides to balance evenly. If you've ever sat on a teeter-totter with a heavier person and a light person on one side, you know the heavier person has to move closer to the center to balance the teeter-totter. The median of the density curve is the equal areas point, right? Halfway through or 50% of the way through. The point that divides the area under the curve in half. So we typically represent the median with the capital letter M. So we've got 2 density curves in the figure below, each with the mean and median marked on them. So for each density curve below, we've got to explain which is the point dividing the graph into equal areas, the median, and which is the balancing point, the mean. So in the first graph, we see there are a few low values, but more of the values are higher. So the few low values pull the average or the mean down. Similarly, you could think, well, there's more area over here where the peak is higher, so our halfway point is going to be closer to the peak. So in this graph, the mean is less than the median. And you'll also notice the tail's coming out to the left. So this is a left tail or left skew distribution. And I remember that it's got a few low values that are pulling this average or the mean down. So the mean is coming out to the left because we've got a left tail with a few small values pulling the average down. The graph at right has the peak over here So that means it's got a higher bars or higher area. So the median here is less than the mean. So in this case, we've got a few high values. Remember, this is the high side of the graph and this is the low side of the graph because we go from smallest to largest. So a few high values are pulling the mean or the average up. So in a right-tailed distribution, where the tail's out here to the right, also called a right skew distribution, we've got a few high values pulling this average or mean up. So question B asks, what's the shape of a density curve where the mean and median are the same value? And it says, make a sketch in the space below. So we know that's got to be where you don't have too much pull in either direction. So that's something where the tails are balanced. So a symmetric or bell-shaped distribution has mean and median both in the center. And here's a picture of what a bell-shaped distribution would look like. So see, here's our mean and median in the center. And you can even see real small, this graph labeled it with the Greek mu down here. And we see it's got balanced tails on both sides, so there's no pull in either direction more. So take a minute and sketch a bell-shaped, sometimes called a normal distribution graph on here. Question C says, in a recent local election, the mean voting age was 56 years old, and the median voting age was 49 years old. What shape is the corresponding density curve? Explain your reasoning. So in this case, in the local election, the median is less than the mean, right? 49 years old is younger than the mean of 56 years old. So using what we know from the graphs in part A, this indicates that a few voters had higher ages, pulling the average of the mean up. So this indicates that the distribution has a right tail, or a right skew, we would say. So in general, the tail is pulled in the direction of the mean. If you look back up here at our graphs, we see the mean is higher. We've got a few high values in the right tail graph, and the mean is lower than the median when you've got a few low values in the left tail distribution. So again, I find it helpful to remember that the tail or the skew is in the direction of the mean.